Welcome to You Got Hope Chemistry. I'm Hope, and you're about to learn some chemistry. So in today's lesson, we're going to focus on doing three different things. We're going to start by reviewing how to get the electric potential of a cell, which you learned in the first lesson, but we're just going to try some questions that are independent of doing all the other stuff that we would have to do on a voltaic cell. Then we're going to look at what is the standard reference half cell and what does that mean. And then we're going to look at questions where the standard reference half cell is changed, and then you're trying to figure out how that's going to affect the question in general. Okay, but the first thing I want to do is just quickly review this equation here, which allows us to calculate the electric potential of the cell. This is something that you do have to memorize. So the electric potential of the cell is equal to the reduction potential at the cathode minus the reduction potential at the anode. So it's obvious that we have to figure out what the anode and cathode are first in the question before we can apply using this equation. Now, please remember that these are reduction potentials. Reduction is the gain of electrons. Reduction, cathode, oxidizing agent. Now, you might go, well, if these are all reductions and I know that oxidation happens at the anode, why am I using a reduction potential? Isn't there something called an oxidation potential? And the answer is yes. The oxidation potential is actually the reduction potential, but with the opposite sign. That's what the purpose of this negative sign is. This negative sign here, or the subtraction sign, this flips the reduction potential to oxidation potentials. Now please, never change this to, say, the electric potential of the cathode plus the oxidation potential of the anode. Everything is done in reduction potentials. We do nothing in oxidation potentials. I want you to use this equation exactly the way it is. I don't want you to change it in any way. Another thing I want to share with you is that let's say you're given an oxidation reaction, half reaction, and it looks something like this. And then they give you an electric potential, and I'm just making something up. Let's say it's positive 1.00 volts. You might think that this is an oxidation potential because this reaction is an oxidation half reaction. This is actually a reduction potential. By IUPAC rules, we write every electric potential as a reduction potential, even if the equation is written as an oxidation half reaction. I know that seems weird, but it's to make sure everybody is on the same page. All electric potentials are always set for reductions, even if you write it right beside an oxidation half reaction. So I'll go through more of this as I go along. It's just kind of this weird nuance that you need to know. So let's start with an easy question, or what I would deem to be an easy question, which is we're given cell notation. So remember, in cell notation, they break the cell into two parts. We have this half cell, and we also have this half cell. Now, if these are written out properly by IUPAC rules, this side has to be the cathode, and the left-hand side has to be the anode side. So what you can do is you can go to your reduction potential table with the reduction half reactions and look up these formulas. Now, you'll see Al3 plus 3 electrons going to Al at an electric potential of negative 1.66 volts. You'll see tin 2 plus 2 electrons becoming tin solid at a negative 0.14 volts. Now, you don't have to show this work. I'm just showing it to kind of teach. But this does confirm that this is the cathode. Negative 0.14 volts is higher up the table than negative 1.66 volts. That means that the oxidizing agent in here, which is this, is closest to the top left-hand corner, which would make this the strongest oxidizing agent. Now, if you're looking at your table as you're watching this, you'll see that the Al is closest to the bottom right-hand corner, which is the strongest reducing agent. And of course, if you lose electrons, undergo oxidation at the anode, that confirms this. You are the reducing agent. If you gain electrons and undergo reduction, this happens at the cathode, and the OA will do this, and sure enough, there's our OA. That has to make this the cathode. Okay, that's enough review. So all I need to do at this point is sub everything into my equation. The electric potential of the cell is equal to the electric potential at the cathode minus the electric potential at the anode. Those are both, again, reduction potentials. So I have a negative 0.14 volts minus a negative 1.66 volts. This negative, of course, is going to turn into a positive. So now my overall cell potential is going to be a positive 1.52 volts. And I can enter that into my numeric response box as 1.52. All right. I would like you to pause the video at this point and try this question. Make sure that you are figuring out what your strongest oxidizing agent and reducing agent is first, in order to figure out the anode and cathode of this net reaction. Please try the question now. Now that you've had an opportunity to try the question, let's go through what we're going to do to figure out what is the OA, the RA, so we can figure out the anode and cathode. There's a number of ways of doing it. When I see acidified dichromate, this is near the top left-hand corner of our reduction half reaction table. I'm pretty sure it's the SOA. The other thing I notice is I've got a solid piece of metal. Metal solids are generally RAs almost all the time, unless they're in some kind of combination with something else. So I'm pretty sure that this is the RA. The other thing I can do is I can use oxidation numbers. So for instance, lead goes from 0 to 2 plus. And in order to do that, you would have to lose 2 electrons, undergo oxidation at the anode, Ra. This would then become my substance at the anode side. And it actually turns out to be the anode. Well, what I'm left with is acidified dichromate, which you can find on your reduction potential table. And it is an oxidizing agent, and it is very, very high up the table. So if you have your reduction table in front of you, you will see this acidified dichromate at an electric potential of positive 1.23 volts. You will see this lead at an electric potential of negative 0.13 volts. So again, this is furthest down the table, so this is going to be my strongest reducing agent, and therefore it's going to be my anode side. So to clarify again, this is furthest up the left-hand side of my reduction half reaction table. This is my strongest oxidizing agent, and therefore this would be the cathode side of the battery. This lead is furthest down on the right-hand side. That makes it the strongest reducing agent, and this is going to be my anode side. So using our basic equation, the electric potential for the cell is equal to the electric potential at the cathode minus the electric potential at the anode. And so I've got a positive 1.23 minus a negative 0.13 volts. If you do that calculation, you get a positive 1.36 volts. Again, the positive means that it's spontaneous. The positive means it's voltaic. The positive means that we have chemical potential energy turning into electrical energy. Placing that into our numeric response box, it's simply 1.36. Okay, so the next thing we're going to look at here is the standard reference half cell. All of the reduction potentials on the reduction potential table have to be referenced against something. There has to be a baseline of 0. Now, the hydrogen half reaction is considered to be the reference half cell. So this one right here. So 2 hydrogen ions accepting 2 electrons, becoming hydrogen gas is 0. So to be clear, it doesn't mean that hydrogen doesn't have an electric potential. It's just the baseline which everything's worked around. So to give you other examples, east meets west in Istanbul, Turkey. Istanbul is a major city in Turkey. East of Istanbul is east. West of Istanbul is considered west. We could easily change that reference. We can make New York, LA, London, whatever city you want to be east and west divide, but that is classically what we've recognized as east and west. Or when we talk about altitude, it's all reference to sea level. But same idea, we could call our reference Denver, Colorado, which is quite high up, and we could base everything around that. We just don't. So hydrogen is the reference half cell. You do need to know this. So this simple reaction, 2H plus aqueous plus 2 electrons becoming hydrogen gas, is called the standard reference half cell. What we're going to do is we're going to look at a couple of different types of questions using the standard reference half cell. One of the questions will be, say, I have a cell and it's made up of tin and copper, but say iodine is maybe the new reference half cell. What would that do to the electric potential? And the simple answer to that is nothing. And we're also going to look at things like, well, let's say silver is a new reference half cell. What would be the reduction potential for the copper half reaction? In this case, we actually do have to make an adjustment. So to repeat, we're going to do 2 different types of questions. We're going to look at questions where we have a new standard reference half cell, and we're asked, say, what happens to the cell potential for a cell made up of these 2 things, say copper and tin. But we're also going to look at questions where they say, we have a new reference half cell, I don't know, maybe nickel. What is the reduction potential for iodine now? And we actually do have to make an adjustment here. All right. So what I'm going to do is we're going to start at one which we actually don't need to make any adjustments, but I think it's important that we actually try the question. So here, this is an example of what I call a distractor. They're trying to get you to bite on something or think that you have to make some kind of change, but you actually don't. So it says, if the standard iodine half cell is chosen as the reference half cell, so this now would have an electric potential set to 0 because it's the reference. Instead of the hydrogen half cell, then the cell potential for a silver nickel cell is blank. All right, the first thing I'm going to do is I'm going to go find silver and nickel up on the chart here, and I'm going to highlight them. So here's silver at 0.8, and here's nickel down at negative 0.26. All right, now let's think about this logically. If I have a new reference half cell, has the physics of the universe changed in any way? I hope you said no. If all of a sudden I made New York east meets west, does the world spin faster or change or do some kind of weird thing? It doesn't. It's just changing a reference. The distance between these 2 electric potentials is the same no matter where 0 sits. So if I have 0 up here, for instance, well, then the distance between these and the difference in their electric potential isn't going to change. Now, I'm just going to use these highlighted half reactions just to make sure we understand what the anode and cathode is so we can finish the question. So silver is the strongest oxidizing agent. This would be gain of electrons, reduction cathode OA. The nickel would be the SRA. This is a spontaneous reaction because the OA is above the RA. This would be losing electrons undergoing oxidation at the anode. All right, so the electric potential for any cell is equal to the electric potential of the cathode minus the electric potential of the anode. So we have a positive 0.80 volts minus a negative 0.26 volts. Our negative has to make a positive, so this would work out to be 1.06 volts. So if you don't believe me that the standard reference half cell being changed has nothing to do with a change in the electric potential of the cell, I'm going to prove that this new reference half cell doesn't do anything in a different way. I'm going to use some math. So in the question itself, it has chosen that iodine is the standard reference half cell at positive 0.54. Now, if it is the reference half cell, you have to set it to 0. So I got to do whatever mathematical operation that will turn this positive 0.54 into 0, which of course would just be to subtract 0.54. So I've set this to 0 volts. Then what I have to do is I have to do this mathematical operation to every other reduction potential in the table, or at least the ones I'm concerned with. So let's say we have this as the new reference half cell and we have a silver nickel battery. What I then have to do is I have to subtract 0.54 volts away from silver, and I have to subtract away 0.54 volts away from nickel, because again, whatever mathematical operation I have to do to set the reference half cell to 0, I have to do it to everything else. But the only two things I really care about right now in this question are silver and nickel. So if you plug that in your calculator, just do a little bit of mental math. This is going to come out to a positive 0.26 volts. This is going to come out to a negative 0.80 volts. So let's have a look. If I have my cathode at positive 0.26 volts, and I subtract away from it a negative 0.80 volts, the positive again, sorry, negative is going to become a positive, and again I'm going to end up with a positive 1.06 volts. So to be as crystal clear as I possibly can, if a question has a full cell, silver nickel, gold copper, tin lead, whatever it might be, but I have an entire cell, and the question says what's the voltage of this cell, if I have a new standard reference half cell, in this case it was iodine, what do I have to do to solve the problem? The answer is nothing that you wouldn't normally do. You solve for it as normal. Creating this new reference half cell just adjusts all these reduction potentials by the same amount. So when you do the difference of those two things, it's going to give you the exact same number. I call this a distractor question. Now, there is a type of question where I do have to make an adjustment, and it is absolutely necessary. So I'm going to read this question to you, and then we'll talk about how it looks different from number 2 here, because there is a big difference. If the reduction of water, okay, I'm going to underline that, reduction of water. Now, reduction is gain of electrons, reduction cathode OA. So I'm treating water as an oxidizing agent, not a reducing agent, because it says it underwent reduction. So if the reduction of water was chosen as the standard reference half reaction, then the electric potential for hydrogen would be, okay. So the first thing I would do is I would go find water as an OA because it's undergoing reduction on my reduction half reaction table, and you will see that its electric potential is negative 0.83 volts. Now, they're not asking in this question what is the cell potential of a cell. They're asking for what is the electric potential for just a half reaction. So I do have to make this adjustment. It's a really easy one to do. Once I set my new standard reference half cell to 0, which is the reduction of water, so I'm going to add 0.83 volts to it to set it to 0 volts. I now know that I have to do this same mathematical step to the hydrogen half reaction in order to figure out its new electric potential. So I look up hydrogen. We should know that hydrogen is an OA as well, and its electric potential is 0.00 volts because it is the standard half cell. I have to do the same mathematical operation to it, so I'm going to add 0.83 volts, and it comes out to a positive 0.83 volts. Putting that in my numeric response box, it's 0.83, and there we go. So just keep this in mind. You always want to do the same mathematical operation to the electric potential for the reduction half reaction. You need to change as to set the new reference half cell to 0. So in this question, we had to add positive 0.83 to everything. In our previous question, if we wanted to solve it mathematically, we had to subtract 0.54 away from everything. This was the same mathematical operation we did to set it to 0. And as long as we do that, we will always get the correct answer. So at this time, I would ask you to pause, and we are going to do some homework questions, but I would like you to try them on your own first. So if you haven't printed off this, here are the questions, one at a time. Pause and try to solve. Pause and try to solve these. All right, I hope you had some success doing those homework problems. Let's go through them and see if you got them correct. So this first one shows a setup of a cell, a voltaic cell. I know it's a voltaic cell because it has a voltmeter and it has a salt bridge. And then it proceeds to say, if the standard silver reduction half reaction has been chosen as the reference half reaction, so this would be set to 0, instead of the hydrogen reduction half reaction, then the electric potential of the cell represented by the diagram above would be. Now, if you were following along before, you know if you have a complete cell and they're looking for the voltage of a complete cell, and they've got a new reference half cell, this silver one, I basically can completely ignore this and solve the problem as normal. And what I mean by that is I would just solve for the voltage of this cell, ignoring completely that there's a new standard reference half cell. If you don't understand why that is, I would rewind the video and go back to the part where I discuss it in the previous page. But what we're going to do now is we need to figure out what is the anode and we need to figure out what is the cathode. Now looking over here, I see I've got nickel and I got nickel 2+. This is a nickel half cell of nickel and nickel 2+. If you go to your data book, you would find this electric potential at negative 0.26 volts. When I look at the other side, I see this platinum thing. Now in our next lesson, I'm going to explain more in detail of these kind of really unique half cells that have things like platinum or carbon electrodes. But essentially this is inert. Its job is to simply conduct, but not to react. So platinum will not react with nitric acid. It's not going to react with anything in this reaction. It's just going to act as an electrode. Now, if you're going, well, why wouldn't I use something else? My answer to you is this. Nitric acid, there is no such thing as solid conducting nitric acid. When I have nickel 2 on the other side, well, nickel solid is a conducting material. It's made of nickel. They can work together in one half cell. There's no such thing as solid nitric acid that conducts electricity. So I need something that's going to conduct electricity, but not be part of the reaction. So what I'm going to do is I'm going to look up nitric acid on my reduction half reaction table. And if you go to an electric potential of positive 0.80 volts, you will notice there's a combination of hydrogen ions and nitrate ions. This is nitric acid as an oxidizing agent, and this actually will be the strongest oxidizing agent in this reaction. The nickel solid here will be the strongest reducing agent. Now, if you want to do this more thoroughly, you could make a species list, and you could write everything out, such as hydrogen ions, nitrate ions, water. We've got potassium in the salt bridge. We got more nitrate. We don't need to write that again. We've got nickel solid. We got nickel 2+. We have platinum, which you're not even going to find on our table. Okay. And sure enough, you do OAs and RAs. This comes out to the strongest oxidizing agent. This comes out to the strongest reducing agent. Now, what that's allowed me to figure out is what is the anode and what is the cathode. So on this side, this platinum would be the cathode, because in this half cell, it contains the strongest oxidizing agent, which is nitric acid. Remember, this electrode doesn't have to be the strongest oxidizing agent. It just has to be in the half cell with the strongest oxidizing agent. Then this is the strongest reducing agent over here, the nickel. So loss of electrons, oxidation anode Ra. And sure enough, this is the anode. So now I can calculate the electric potential the way we've been doing for quite some time. I'm simply going to say the electric potential of the cell is equal to the electric potential at the cathode minus the electric potential at the anode, which is a positive 0.80 volts for nitric acid minus a negative 0.26 volts for nickel, and it comes out to a positive 1.06 volts again. I didn't do this on purpose. These are real diploma questions. 1.06. All right, for our next question. This question says, if the nickel half reaction is designated as the reference half reaction, so we have to set that to 0, then the electric potential for the iron 3 to iron 2 half reaction is. Now this question is different than the previous one. In the previous one we had a cell and they want to know the cell potential. Here we have a new reference half cell and they're asking for the electric potential of just a half reaction, not an entire cell. I do have to make a mathematical correction for this or it won't work out. So step number 1 is always to set something to 0. So if I look up the electric potential for nickel, it's set to negative 0.26 volts. I have to first then set this to 0 by doing a mathematical operation that will set it to 0. This would be to add 0.26 volts. Now I've set this to 0 volts. I do this mathematical operation to everything else or just whatever I'm concerned about in the question on that reduction half reaction table. So step number 2, I'm going to take the electric potential for the iron 3+ to iron 2+ half reaction. So I go to my table, I look it up, and it is at a positive 0.77 volts. I'm going to do the same mathematical operation to it. So positive 0.26 volts. And I get a voltage of 1.03 volts, which would be A. Number 3 is very similar to number 2. So in the question it says, if the copper 2 to copper reduction half reaction was assigned the reduction potential of 0 for an electrode potential table, then the nickel 2 to nickel half reaction on the table would have the reduction value of. Okay, I first, number 1, need to set copper to 0. So the electric potential for copper on the table is a positive 0.34 volts. I'm then going to perform a mathematical operation to set it to 0. So subtract 0.34 volts. So this is 0.00 volts. In step number 2, I'm going to look up the electric potential for nickel. I've done that several times now, so I do know it's negative 0.26 volts. I want to do the same mathematical operation to nickel as I did to copper. So minus 0.34 volts. And sure enough, it comes out to a negative 0.60 volts. And our answer is D. I hope you've enjoyed this lesson. See you next time on You Got Hope Chemistry.